Welcome to Chapter 7, Section 1, Nth Roots and Radical Exponents. In this lesson, we're going to evaluate nth roots of real numbers using both radical notation and rational exponent notation. So I want you to take a couple seconds, write down these 4 bullet points here when we're talking about nth roots. Okay, so pause the video real quick and write down what I have here in this chart. Okay, hopefully you have everything written down now so we can talk about what this says. First off, when we're talking about nth roots, this n that we're saying here, first it's going to be an integer greater than 1. And what we call this an index. So when we deal with these roots, the n, that number, we'll refer to it often as an index. And so, like I mentioned, the number has to be an integer, meaning it has to be 1, 2, 3, 4, 5, 6, or the negative counterparts. But typically we want it greater than 1, and we want a to be a real number. Alright, so we're not dealing with I here, no imaginary numbers, only real numbers for this part. So there's a few rules here. First off, if n is odd, then a has one real nth root, and this is important here. So for all odd indices, a only has one real root. Alright, so and how we read this notation here, this is the nth root of a, or in other words, we write it as a to the 1 over n. That power, that rational exponent, 1 over n, is another way of writing our radical notation. Now, if you're wondering where this rational notation comes from, there is a simple yet elegant proof on page 401 of your textbook. I'm not going to go over it right now. If you have questions, you can ask me in class, or you can review it on your own. But there is a proof of why this is true here. Okay, so if n is odd, there's one real root. But if n is even, we have a few different cases here. Alright, if n is even and a is greater than 0, meaning a is positive, then a has 2 real nth roots. And those nth roots are going to be plus or minus the nth root of a, or plus or minus a to the 1 over n. And we'll get some examples here to nail down what I'm talking about in a second. So that's if n is even and a is positive. Well, if n is even and a is 0, then there's only one nth root. And that's 0, because the square root of 0, the third root of 0, the fourth root of 0, any root of 0 is always going to be 0. So that's a special case for even roots. And when you take that even root of 0, it's always going to be 0. If n is even and a is negative, then there are no real nth roots. And you already know this. What we studied last chapter, we talk about the square root of -4. Well, we know we can evaluate that and say that that's just going to be 2i, but when we deal with real numbers here, that's not a real number, that's an imaginary number, and so we say that there are no real roots when our radicand is a negative. Okay, so let's deal with some numbers here and practice a few of these indices here. Alright, so in this example we have an n of 3 and an a of -125. So we're asking ourselves, what is the third root of -125? And there's 2 ways we can write that. We can write that as -125 as our radicand inside of a third root, or a cube root. Now another way to write that is -125 raised to the power of 1/3. In either case, we can evaluate this and ask ourselves, well, what number would we have to cube to get a -125? So that number, there's only one, knowing that this index here is odd. Alright, we know there's only one real answer, and that's -5. So -5 cubed is -125, so therefore the cube root of -125 is -5. Look at another example here. We have the fourth root of 16, or we can write it as 16 to the 1/4. So we're asking ourselves, what number can we raise to the power of 4 and get 16. Now remember, 4 is even, so there's going to be two separate answers here. We're going to have a positive and a negative root for the fourth root of 16. Well, if you use your head a little bit, think through some numbers here, you know that 2 raised to the fourth power will give us 16. But remember, we have to have both plus or minus. So both a positive 2 raised to the fourth power and a negative 2 raised to the fourth power yields 16. So the solution to the fourth root of 16 is plus or minus 2. There are two answers. Now, let's look at a few properties of irrational exponents here. All right, if we have just 1 over n, that's the nth root of a number, and we saw that just a few slides ago when dealing with the cube root, dealing with the fourth root. All right, but what happens if our numerator of a rational exponent is not 1? So if we have a raised to some power of m divided by n, and assuming that both m and n are positive integers, what this means, we can use a little algebra here, split this up into a to the 1 over n, meaning the nth root of a, raised to the power of m. So we can do these two separate exponents separately. Now, even though I have it pictured here as a to the nth root and then raised to the power of n, it doesn't matter which order you do it. You can raise a to the power of n, and then take the nth root. All right, so let's look at a few examples. For instance, 9 to the 3 halves. Okay, so what this means, 9 to the 3 halves, well, we can rewrite this as 9 to the 1 half, and that quantity raised to the power of 3. Well, we know 9 to the 1 half is just the square root of 9, and we want to raise that to the power of 3. Well, the square root of 9, is 3, and 3 cubed is equal to 27. So 9 to the 3 halves is equal to 27. All right, take a look at this one. 32 raised to the negative 2/5. Okay, so once again, we want to rewrite this. Knowing that this exponent is negative, that means it's the inverse of the reciprocal of the positive exponent of 32 to the 2/5. And we know 32 to the 2/5 can be rewritten as 32 to the 1/5, and then that quantity squared. Well, we ask ourselves, well, what's the 5th root of 32, or what number can we raise to the power of 5 and get 32? And that's going to be 2. So 1 over 2 squared, sorry, my pen's acting up, 1 over 2 squared is equal to 1/4. So 32 raised to the negative 2/5 is equal to 1/4. All right, now how are we going to use these roots? Well, we're going to use these roots to continue to solve higher order polynomials. All right, last chapter we learned a few methods in solving higher order polynomials, such as factoring special cases and using the rational root theorem. Well, we're going to look at some more special cases that we can take quicker shortcuts, such as if we have 2x to the 4th is equal to 162. All right, well, 2x to the 4th, we can isolate x by dividing by 2 first and getting x to the 4th is equal to 81. Well, we could bring the 81 over and try to factor or use the rational root theorem and go through all the stuff we did in chapter 7, which would still work and would still yield the correct answers. But we can also just notice that since we only have x to the 4th and it's equal to a rational number, we can just take the 4th root of both sides. All right, now the 4th root of x to the 4th is simply x. But the 4th root of 81, you have to ask yourselves, well, what do I raise to the 4th power to get 81? And that number is going to be 3, but we have to be careful. Since we're taking an even root, our index is even, we need a plus or minus, because both positive 3 to the 4th power and negative 3 to the 4th power yields 81. a positive 81. So when you take an even root, you need the plus or minus there. So in this polynomial, this quartic, x can either equal 3 or negative 3. All right, take a look over at this second example in part B. If we have the quantity x minus 3, we have the quantity x minus 2 raised to the third power, and that's equal to 10. Well, just like we did over here, we want to isolate x, and first we can take the cube root of both sides, or we can look at it as raising to the power of 1/3, either way. So you can write x minus 2 cubed, raise that entire quantity to the power of 1/3. And this can kind of prove to you that it does cancel out, because 3 times 1/3 is 1, and anything raised to the power of 1 is just itself. So we end up getting x minus 2 is equal to the cube root of 10. And since 10 is not a perfect cube, we're going to leave this as an exact answer and just leave it as the cube root of 10. Now you might ask, why is there not a plus or minus here? Well, remember, this is an odd root, and odd roots only yield one real answer. Even roots, you can have 2. Odd roots only have 1. So to finish solving this, we get x is equal to 2 plus the cube root of 10. All right, so the only real answer to this is 2 plus the cube root of 10. All right, one last problem here. We're going to look at a word problem dealing with solar sails. Okay, so the total mass, big M, the capital M, in kilograms, of a spacecraft that can be propelled by a magnetic sail is, in theory, given by capital M equal to 0.015 little m squared divided by the quantity of F times d to the 4/3, where the lowercase m is the mass in kilograms of the magnetic sail, F is the drag force in newtons of the spacecraft, and d is the distance in astronomical units to the sun. Find the total mass of the spacecraft that can be sent to Mars using m, little m, of 5,000 kilograms, so that's the mass of the sail, a drag force of 4.52 newtons, and a distance of 1.52 astronomical units. Okay, so we look at this, we see the variables we have this little m, we have the f, we have the d, so we have these 3 variables that all we have to do is substitute in, and we can find the total mass in kilograms of our spacecraft. So let's write our equation. M is equal to 0.015 m squared over f d to the 4/3. Okay, let's plug in the information that we had. We know the 0.015 coefficient is going to stay there. We have a mass of the sail of 5,000 kilograms. That's going to be raised to the second power. We're going to divide that by 4.52 newtons multiplied by the 1.52 astronomical units, but we want to raise that to the power of 4/3. All right, now tomorrow I am going to work with you a little more on how to properly put these rational exponents into your calculator. But if you put all this into your calculator and you do it correctly and use the correct order of operations, you should get about 47,500 kilograms. So I want you to play with that a little bit, try to figure out how to properly put in the exponents and do the correct division and multiplication in order to get 47,500 kilograms. Now, to give you some perspective, an average spacecraft at takeoff is about 2 million kilograms. And so from takeoff to just the spacecraft needing to be propelled by the sail, you'd have to cut down pretty drastically. That's why we don't have any of these in production yet. So take a look at some of the homework from this section. Come in tomorrow with any questions, issues, or concerns that you may have, and I hope this video helps.